Hello friends, myself Anjali Shinde, Associate Professor, Department of Mathematics, S.V.K.T College, Devali Camp, Nasik. In the previous lecture of calculus, we have studied Rolle's theorem. It states that if a function f is continuous on closed interval ab, derivable on open interval ab, and if fa is equal to fb, then there exists at least one point c belonging to open interval ab such that f dash c is equal to 0. Today we are going to see one of the consequences of this Rolle's theorem known as Lagrange's mean value theorem. This is also known as fundamental mean value theorem or simply mean value theorem. The theorem states that if a function f is continuous on closed interval ab, it is derivable on open interval ab, then there exists at least one point c in open interval ab such that f dash c is equal to fb minus fa upon b minus a. To prove this theorem, we define a function phi on closed interval ab as phi x is equal to fx minus ax, where a is nothing but the constant to be defined such that phi a is equal to phi b. Now, if phi a is equal to phi b, then from our definition of phi, what is phi a? That is replace x by a. It is nothing but fa minus aa. It is same as phi b. It is nothing but fb minus ab. So, substituting the value of x to be a and b, we get phi a and phi b from our definition of phi. Simplify this. This implies that fa minus fb is equal to a into bracket minus a into bracket b minus a, or we have a is equal to fb minus fa upon b minus a. Now observe our definition of phi. It depends on fx and it is a linear combination of this. So phi x is fx minus ax implies that phi is obviously continuous on closed and bounded interval ab. It is derivable on open interval ab, and also we have defined phi a is equal to phi b, means that phi satisfies all conditions of Rolle's theorem. And therefore, by Rolle's theorem, there exists at least one point c in open interval ab such that phi dash c is equal to 0. Now we know phi x. So what is phi dash x? So from this one, we get phi dash x, and phi dash x is nothing but f dash x minus a. So that replace x by c, we get phi dash c, which is nothing but f dash c minus a. But we have phi dash c is equal to 0, and therefore we get 0 is equal to f dash c minus a, that is we get a is equal to f dash c. Observe, we get the value of a to be fb minus fa upon b minus a, and we also have the value of a to be f dash c. So from comparing both these equations, we get f dash c is equal to fb minus fa upon b minus a. That completes the proof of the theorem. So we have f dash c is equal to fb minus fa upon b minus a. So see, for proving this Lagrange's mean value theorem, we have used Rolle's theorem. So it is one of the consequence of Rolle's theorem. Now observe, if you have fa is equal to fb, that is, in Rolle's theorem we know that if these 2 points are equal, if fa is equal to fb, then obviously we have f dash c is equal to 0. So Rolle's theorem can be obtained from this. By taking the condition fa is equal to fb, we get f dash c is equal to 0. So this is Lagrange's mean value theorem. The conditions are that the function must be continuous on closed and bounded interval and derivable on open interval. Then there exists such point c which satisfies the condition f dash c is equal to fb minus fa upon b minus c. Now what it geometrically means? It geometrically means that if we have the curve y is equal to fx, between these 2 points a and b, suppose this is the curve y is equal to fx, then there is at least one point c in the interval ab such that the tangent at this point c to the curve y is equal to fx is parallel to the line segment joining the points afa and bfb. So this is the point bfb and afa. This is the line segment joining the points afa and bfb, and this there is at least one point c such that the tangent drawn at this point to the curve is obviously parallel to the line segment joining. There is at least one point. There may be more than that, but there is at least. This is also point. If you draw a tangent at this, the tangent will be parallel to the line segment joining AFA and BFB. Or there is again a point such that the tangent at this point will be parallel to the line segment. So the theorem says that there is at least one point C in the open interval AB such that the tangent drawn at that point to the curve is parallel to the line segment joining AFA and BFB. Now we will see one of the consequences of this Lagrange's mean value theorem, which gives us a definition or criteria for constant function. So the theorem says that, or it may be seen as corollary, it says that suppose f is continuous on closed and bounded interval AB and derivable on open interval AB, and if f dash x is equal to 0 for all x belonging to AB, then f is constant in the interval AB. So let us prove this theorem. It is given that it is continuous in closed interval and derivable in open interval. One more condition is given. For every point x in the interval AB, f dash x is equal to 0. So x belongs to this open interval AB. So consider the interval AX. Obviously, as the function is continuous on this interval AB, what happens? F is obviously continuous on closed interval AX, as x lies in AB and it is continuous on closed interval AB. So it is continuous on AX also. It is derivable on open interval AB. So it also implies that it is derivable on open interval AX, and hence F satisfies Lagrange's mean value theorem. In short, we denote it as LMVT. F satisfies Lagrange's mean value theorem. So what is our Lagrange's mean value theorem? There exists at least one point C in open interval AX such that f dash c is equal to fx minus fa upon x minus a by LMVT. Since f satisfies all the conditions of Lagrange's mean value theorem, there exists at least one point C in open interval AX such that f dash c is equal to fx minus fa upon x minus a, or cross multiplying we get fx minus fa is equal to f dash c into bracket x minus a. But see what is given to us. It is given that f dash x is 0 for all x in AB. Since c belongs to in the interval, this means that f dash c is also 0. So from given condition that f dash x is 0 for every x, we have f dash c is equal to 0, and therefore we have fx minus fa is equal to 0, because f dash x is 0 for every x in AB implies that f dash c is also 0, and therefore we have fx is equal to fa. Fx is equal to fa means that f is constant function. So on this interval AB, obviously f becomes constant function since it takes the value fa for every x, and therefore f become constant function. So this is one of the consequence of Lagrange's mean value theorem, that if for every point in AB f dash x is 0, then f becomes constant function on that interval. Now let us consider some examples depending on this Lagrange's mean value theorem. Verify Lagrange's mean value theorem for fx is equal to log x on the interval 1e. We want to verify Lagrange's mean value theorem. We know that what are the two conditions of Lagrange's mean value theorem? The function must be continuous on closed interval and derivable on open interval. Observe that fx is equal to log x. It is continuous on this interval and also derivable. So we have fx is equal to log x. Therefore, f is continuous. Being logarithmic function, it is continuous on closed interval 1e and derivable on open interval 1e. What is f dash x? Because fx is equal to log x, f dash x is nothing but 1 upon x. So f is continuous also on closed interval, derivable on open interval. So both the conditions of Lagrange's mean value theorem are satisfied. Hence, by Lagrange's mean value theorem, there exists at least one point C in open interval 1e such that f dash C is equal to Fe minus F1 upon E minus 1. Now what is f dash x? 1 upon x. So what is f dash c? It is 1 upon c. So 1 upon c is equal to Fe, that is log e minus log 1 upon e minus 1. This implies 1 upon c is equal to 1 upon e minus 1, or cross multiplying give c is equal to e minus 1. Observe that this c point lies in the interval 1e. See that this value e minus 1 obviously belongs to the interval 1e, and hence LMVT is verified. We want to show that this c value lies in the interval 1e. Because the value is e minus 1, it obviously lies in the open interval. Hence, Lagrange's mean value theorem is verified. So, given the conditions are satisfied, there surely exists at least one point in this open interval, that is LMVT is verified here. Now, this LMVT can be used to show some inequality. We want to prove that if A is less than 1 and B is less than 1, and also if A is less than B, then B minus A upon root of 1 minus A square is less than sin inverse B minus sin inverse A is less than B minus A upon root of 1 minus B square. Using Lagrange's mean value theorem, we are going to prove this, that B minus A upon 1 minus A square is surely less than this value sin inverse B minus sin inverse A, and it is less than B minus A upon root of 1 minus B square. So, we will start with our function fx is equal to sin inverse x. We will take this function from this. We will guess that the function is fx is equal to sin inverse x. Observe that sin inverse x being the inverse trigonometric function, it is continuous on domain and derivable also, and therefore it satisfies Lagrange's mean value theorem. Now what is f dash x? F dash x is nothing but 1 upon root of 1 minus x square. Being inverse trigonometric function, as it satisfies Lagrange's mean value theorem conditions, by Lagrange's mean value theorem, there exists at least one point C in the interval AB such that f dash C is equal to FB minus FA upon B minus A. But what is f dash C? We know f dash x. F dash x is 1 upon root of 1 minus x square. So, replace x by C. What is f dash C? It is 1 upon root of 1 minus c square. FB, fx is sin inverse x. So, FB is nothing but sin inverse B. FA is nothing but sin inverse A upon B minus A. So, we get the value of 1 upon root of 1 minus c square. Now, observe that C lies between A and B. So, it is given that C belongs to open interval AB, means that A is less than C is less than B. This implies that A square is less than C square is less than B square. But we require minus C square. So, we multiply by minus. When you multiply by minus, the inequality will be changed. So, it becomes minus B square. Now, add 1 on everywhere. So, we get 1 minus A square is greater than 1 minus C square is greater than 1 minus B square. Take reciprocal. So 1 upon 1 minus a square, the inequality gets upon less than 1 minus c square less than 1 minus b square. Taking square root, we get 1 upon root of 1 minus a square is less than 1 upon root of 1 minus c square is less than 1 upon root of 1 minus b square. But observe, by 1 we know that what is 1 minus c square, 1 upon root of 1 minus c square. So put that value here. So by 1 we get 1 upon root of 1 minus a square is less than the value of 1 upon root of 1 minus c square is nothing but sine inverse b minus sine inverse a upon b minus a, and it is less than 1 upon root of 1 minus b square. This we get by 1. And therefore cross multiplying we get b minus a upon root of 1 minus a square is less than sine inverse b minus sine inverse a is less than b minus a upon root of 1 minus b square. So observe that Lagrange's mean value theorem can be used to solve such examples. So it is given that a is less than b. We take the function fx is equal to sine inverse x. Being inverse trigonometric function, it satisfies Lagrange's mean value theorem, that is continuity and derivability on closed and open interval respectively, and therefore we get f dash c is equal to ab minus ap upon b minus a. As c lies in the interval ab, we have the condition we want value of 1 upon root of 1 minus c square. So accordingly we consider the steps and we get the value of 1 upon root of 1 minus c square as sine inverse b minus sine inverse a upon b minus a. So we are able to prove that b minus a upon root of 1 minus a square is less than sine inverse b minus sine inverse a is less than b minus a upon root of 1 minus b square. A similar example is there. If a is less than b, we want to prove that b minus a upon 1 plus b square is less than tan inverse b minus tan inverse a is less than b minus a upon 1 plus a square. So it is similar like last example. To prove this, we will start with fx. Fx is equal to tan inverse x. Again, the function is continuous on closed interval ab and derivable in open interval ab, being inverse trigonometric function, and therefore fx satisfies conditions of Lagrange's mean value theorem. What is derivative? Tan inverse x, it is 1 upon 1 plus x square. Now as it satisfies Lagrange's mean value theorem, by theorem there exists at least one point C in open interval AB such that f dash C is equal to FB minus FA upon B minus A. But what is f dash c? Replace x by c here. So f dash c becomes 1 upon 1 plus c square. Fx is tan inverse x. So fb is tan inverse b minus fa is tan inverse a upon b minus a as it is. So we get 1 upon 1 plus c square is equal to tan inverse b minus tan inverse a upon b minus a. Now observe that this c lies between AB, means that A is less than C is less than B. We want to see what is the value of 1 upon 1 plus c square where it lies. So we go up to this. So we required c square. This implies us a square is less than c square is less than b square. Adding 1, we get 1 plus a square is less than 1 plus c square is less than 1 plus b square. Or taking reciprocal, 1 upon 1 plus a square is greater than 1 upon 1 plus c square is greater than 1 upon 1 plus b square. That is 1 upon 1 plus b square, it is less than 1 upon 1 plus c square, it is less than 1 upon 1 plus a square. Observe, this 1 upon 1 plus c square lies between 1 plus b square, 1 upon 1 plus b square and 1 upon 1 plus a square. So from 1 we substitute the value of 1 upon 1 plus c square. So what we get? 1 upon 1 plus b square is obviously less than tan inverse b minus tan inverse a upon b minus a. It is less than 1 upon 1 plus a square. Cross multiply, we get b minus a upon 1 plus b square. It is less than tan inverse b minus tan inverse a. It is less than b minus a upon 1 plus a square, which is nothing but what we want to prove. So we are able to prove that b minus a upon 1 plus b square, it is less than tan inverse b minus tan inverse a is less than b minus a upon 1 plus a square. So these are some examples on Lagrange's mean value theorem. So today we have seen what is fundamental or Lagrange's mean value theorem. It may be known as simply mean value theorem. It states that if the function f is continuous on closed interval ab and derivable on open interval ab, then there exists at least one point c in open interval ab such that f dash c satisfies the condition f dash c is equal to fb minus fa upon b minus a. Geometrically it states that there is at least one point c on the curve y is equal to fx such that the tangent drawn at that point to the curve is parallel to the line segment joining the points AFA and BFB. We have also seen some of the applications of Lagrange's mean value theorem to show how to prove f is constant when f dash x is 0 for every x in AB and some examples on it. In the next lecture, we will see Cauchy's mean value theorem. Thank you.